Today we're going to talk about properties of exponents. As you can see, there are a fair amount of them here, but some of them do kind of flow together, so it's not quite as bad as it looks, I would say. The nice thing with properties of exponents, as you'll see once we get done going through all of them and actually start using them in examples, is there is not a certain order that you have to use them, right? Like with addition, subtraction, multiplication, division, you have your order of operations, right? You have PEMDAS, maybe you've learned, parentheses, exponents, multiplication, division, then addition and subtraction, that kind of thing. Properties of exponents are all essentially in the same step for order of operations. So when you are trying to simplify the expressions that we're going to look at later using these properties, you're not going to have to worry about am I going in the correct order. You can pretty much just look at whatever expression you're given, and if you see a property that can be used, you can use that property. It doesn't matter what order you do stuff in. So that should hopefully be looked at as a nice thing. Now what that does mean is if you are working on properties of exponent stuff with classmates, you guys can have problems that look different from each other but can still end up with the right answer at the end, so it is harder to check with each other. But looking through these properties, product of powers is our first one. Basically what product of powers is saying, what I want you to notice here, is notice that we have the same base in each of our terms. Remember there are two vocabulary words to remember. The base is the bigger number, the number that's on the ground level, and then your exponent is that tiny number up above, right? Like if we have x squared, x is the base, and that 2, the part that is squaring it, that 2 is the exponent. So make sure you know those two words. So a is our base in this example. Notice that they are both the same base of a. What's different is that one of them has an exponent of m, and one of them has an exponent of n. And so what the product of powers says is if your two bases are the same, if you are multiplying like bases, then you can add the exponents together. Meaning, say we did have an x squared, and we wanted to multiply that by x to the third. Since they both have a base of x, we can take x squared times x to the third, and we would get x to the fifth, because 2 plus 3, adding those two exponents together, gives us 5. Now our second property is the quotient of powers. That is effectively the same idea as product of powers. It's just recognized that instead of multiplying our two bases, we are dividing our like bases. So, to me, I think it logically flows that when we multiplied like bases, we added the exponents. So when we divide like bases, we need to subtract the exponents. Meaning, if I asked you to take x to the third, sorry, that's a bad 3. If I asked you to take x to the third divided by x squared, again, it's important that we recognize that both of these have a base of x, and that's why this property works. Since it's an x divided by an x, we can simply subtract the exponents. And since 3 minus 2 is 1, we would get x to the first. So product of powers, quotient of powers, they are two different properties, but I do think they have relationship with each other, right? They are connected to each other. I don't really view it as two separate things I have to memorize necessarily. Moving on to power of powers. The thing to notice with power of powers versus the last two is that here we have one base but two exponents going to it. Alright, meaning notice in our first two properties we had two separate terms. We had a base with an exponent, and we had a second base with an exponent. With the power of powers, we are now looking at one single base, and it has two exponents going to that same base. And so what that does is when you have a power to another power, or when you have two exponents going to the same base, you are going to multiply those two exponents. Meaning, instead of having an x squared and an x to the third, let's say you were asked to take x squared to the third, meaning now both that 2 and 3 exponent are going to the exact same base. So now it's not an issue of do I add or subtract. Now you would multiply 2 times 3 to give you x to the 6th. So that's the key there. You want to pay attention. The key thing to be looking for when you're using properties of exponents is when you have multiple exponents, do they each have their own base? Or do you have multiple exponents trying to get to the same base? Let's look at our fourth property here, power of product. I think really power of product is just an extension of power of powers because it's really the same idea. Because remember, if you are not shown an exponent, what does any term without an exponent really have there? Well, it has a 1, right? When we write x, that's the same thing as x to the first. If you write a 2, that's the same thing as 2 to the first. The same way that if we write x, we don't actually always write that one coefficient, but if you aren't shown a coefficient, there's always a 1 in front of that x, right? And the same way there's always an invisible 1 in front of that x, there's always an invisible 1 for the exponent unless we specify otherwise. So when we're looking at power of a product, we're looking right here at power of a product, we have an a to the first and we have a b to the first. And what this is saying is when you look at this, yes, you have an a and a b, but both of them are being taken to the m power. And so basically this is almost just distributive property for exponents because we're going to take m times 1 and m times 1 for both of these to give us a to the m and b to the m. Meaning it's basically the same idea as power of powers, where we said if we have two exponents going to the same base, you have to multiply them. It's just what happens if you have multiple bases that both have multiple exponents. So I know that sounds confusing, but think about it this way. Let's say we had x squared y. We'll say x squared y to the third. And I asked you to take those to the fourth power. Okay, I'll erase this to give us some more space here. If we took x squared y to the third to the fourth power, well, what's happening there, if we just focus on the x to begin with, if we just focus on the x, that x is being both squared, taken to the second power, and being taken to the fourth power. And as we just learned from our power of powers property, if I have two exponents that are both going to the same base, I'm supposed to multiply those exponents together. So if both the 2 and the 4 exponent are going to x, that means I need to take 2 times 4 to give me x to the 8th. Likewise, with this y term here, focusing on just the y term now, that is being both taken to the third and taken to the fourth. So if the y base has two exponents going to it in both the 3 and the 4, then we need to multiply 3 times 4 to give us y to the 12th. That's what the power of product is saying. I know it's a little out of order from what I have written here, but I would also draw your attention down here to power of a quotient. It's effectively the same thing. It's just for whenever you have a fraction. And what it's saying is, hey, if you have two terms in a fraction, and they both have multiple exponents going to them, you can just take the exponent to each of them separately. Meaning, if we had x squared over y to the third, and all of that was being taken to the fourth, well, you have an x squared to the fourth, and so that's two exponents to one base of x, so 2 times 4 is 8. And you also have a y to the third to the fourth, meaning that y base has two exponents of 3 and 4, so 3 times 4 would give you 12. And you'd end up with x to the 8th over y to the 12th. I know that was a little out of order from how I wrote these, but I think those kind of go together. Anyways, let's look at these last two then, saving the easier ones for last, I think, so since I know that all of these properties can be a little overwhelming at times. If we look at the last two here, we've got negative exponents and zero exponents. Negative exponents are pretty straightforward. You shouldn't have them. You should not ever have a final answer where you leave an exponent negative. You can always change it to being positive, and that is what is preferred and more than likely expected from whatever teacher you have. Basically what it boils down to is if you have a negative exponent, you want to find its reciprocal. Meaning, if the term was in the numerator, you need to move it to the denominator. If the term was in the denominator, you need to move it up to the numerator. So the example we have here is we have an a to the negative m power. Well, that's not being expressed as a fraction right now, and so if it's not expressed as a fraction, we would assume that's in the numerator. So we would want to flip that and move it to the denominator. For example, let's say you had x to the negative second. Well, if that's not written as a fraction, then that means we assume it's in the numerator, right? Because that means if we wanted to make it a fraction, we would put it over 1. Since it's a negative exponent, I don't want to leave it in the numerator, and so I simply find its reciprocal, meaning I move it down to the denominator, and that gives me a positive exponent. That's effectively what that property says. So to maybe give a little bit of a better example with some more terms, let's say you had x to the negative second, y to the third, and z to the negative fourth. So we would look at each of these terms separately, and I would say, okay, I can see that x currently is a negative exponent. So to fix that, I'm going to move it from the numerator down to the denominator. That allows it to be positive. I see that my y has a positive exponent already, so I'm just going to simply leave y to the third where it was. It already had a positive exponent, it has nothing wrong. Z, I see, has a negative exponent, but it was in the denominator already. So that means to find its reciprocal, I would be flipping it from the denominator up to the numerator. That would cause it to be positive. And so this would be our simplified version of what we started with. That's what the negative exponent property is trying to say. Last but not least, we have the zero exponent property. It really is as straightforward as it shows there. Anything to the 0 power is 1. Period. That's truly all it is. Anything to the 0 power is 1. Meaning even if I come up with some crazy long thing like that, if I take all of this and say all of this is to the 0 power, your answer is simply 1. Anything to the 0 power is just 1. So really the only tough part with that is I know sometimes people want to reflexively say anything to the 0 power is 0, and that is not the case. Make sure that you say anything to the 0 power is 1. Otherwise, those are your properties of exponents. So let's look at an example here of a problem or an expression that we want to simplify here using our properties of exponents. So we've got 4a to the third b squared times 3a to the negative fourth b to the negative third. Right off the bat, we've got 4 times 3. There's no exponents going on with those. They don't have any extra exponents than just their regular, to the first power. And they don't have any other powers going to them anywhere. So 4 times 3 is 12. You really can just keep it as simple as that. 4 times 3 is 12. We're done with the number part of this. So then, let's take a look at our a terms. I have an a to the third being taken times an a to the negative fourth. So if we think about our exponent properties, if we are taking an a to the third times an a to the negative fourth, that is taking two terms with like bases and multiplying them together. So thinking about our very first property, product of powers, right here, product of powers, if we think about that, we are told, or we've learned that we are supposed to add the exponents when we are multiplying like bases. So the question is, what is 3 plus negative 4? Because that's effectively what we're doing, right? If we are taking a to the third times a to the negative fourth, that means we want to take a to the 3 plus negative 4. Well, 3 plus negative 4 is negative 1, so we would have a to the negative first. Likewise, we want to do the same thing with our b terms, because we have a b squared times a b to the negative third. Well, again, that would mean we are multiplying like bases. So since we have two separate b terms with their own exponents, if we want to multiply those like bases together, we want to add their exponents. Meaning, if we're taking b squared times b to the negative third, we are looking to do b to the 2 plus negative 3. 2 plus negative 3 would be, again, negative 1. So we have a b to the negative first. Now we did successfully combine these two terms into one, but we are not done with this problem. This is not fully simplified. And the reason for that would be we have negative exponents still. And like I said earlier, we do not want to leave answers with negative exponents in them. It is important to remember here that 12 is its own part, its own factor, and it has its own exponent of 1. We have a 12 to the positive first, an a to the negative first, and a b to the negative first. It's important you remember the numbers are their own thing. So when I'm looking at what I'm going to have to do, the 12, being as it's to the positive first, it's fine where it's at. 12 doesn't need to have anything done to it. It's all good. The a and the b, those are the negative exponents that we need to deal with. Since they're negative exponents, we know from our properties we need to find their reciprocal. Or in other words, since they were in the numerator with 12, we need to move them down to the denominator. Once we've done that, that changes those negative 1 exponents to positive 1 exponents. It's up to you whether you want to write those exponents there, or since it is just a 1 exponent, we know that if we don't write an exponent, it is assumed that they are to the first. So you could also just leave them without the ones at all and call that a final answer. Either one would work just fine. Let's look at another example. Let's say I gave you 4r to the 0 power to the 4th. So again, it's important that you recognize 4 is its own thing. 4 has an exponent of positive 1. It didn't show us an exponent, which means there's just an exponent of positive 1 there. R, we can clearly see, has its own exponent of 0. And this is being taken to the 4th. This is a good example of what I was talking about at the beginning when I said it doesn't matter what order you use your properties in, because we have a couple different properties we could look to start with here. One option would be to deal with that 0 exponent immediately. We know from the 0 exponent property that anything to the 0 power is simply 1. So we could say our next step is to change r to the 0 into just 1. And 4 times 1 is just 4, so that means really all we're doing is taking 4 to the 4th power. Now, in general, I can't speak for every single teacher, but in general, if you have a number like this that you can actually simplify by just tossing into a calculator, generally they're going to ask you to do that. So I would not say 4 to the 4th is a final answer. I would say 256, what 4 to the 4th power actually is, would be your final answer, just for the record. What I also want to point out, though, is that's not the only way that you could solve this problem out. You could also look at this as power of a product, where we have two terms inside the parentheses, and we need to distribute effectively this 4 exponent to both of them. So 4 times 1 would give us 4 to the 4th, and 4 times 0 would give us still r to the 0. Then we could say, okay, r to the 0, well, anything to the 0 power is 1, so that means we really have 4 to the 4th times 1, which is really just 4 to the 4th, and that's where we get our 256 from. You see, we get the same answer either way, and it truly doesn't matter which way you go. I think you could definitely argue the way we did it first is probably the easiest way, but it really doesn't matter which way is easiest. It's whatever you see. When you're doing these yourself, it's whatever you see when you're working through these. That's what you should choose to do. That's the great thing about properties of exponents, is whatever property you see that you can use, just use it.
It'll work out eventually once you work. It just depends on how long it takes you to work your way through it. That's the only thing that'll be different.